Here we go. We're on this journey of integral calculus. Integral calculus. You know how fast something is changing? You want to know how much of it there is. You know how fast something is changing. So we have a rate of change function. At any given value of input, that function tells us what the rate of change is at that moment. All right, and so a graph is one representation of a rate of change function. Given any value of input, the y value of the point on the graph is the rate of change of some quantity at that value of input. And this example was the sand unloading example. Sand unloading. So our input quantity was time in seconds since the sand first hit the weight scale. And then the output here would be the rate of change. Y values on this graph would be the rate of change of sand in hundreds of pounds per second. Okay? And so we know how fast something's changing. We want to know how much of it there is. Well, that's our accumulation function. So, and I'm showing you now, an exact accumulation function. This is no longer a piecewise linear function. This is a curve. That's the exact accumulation function corresponding to this rate of change function. So what are y values on this graph? What are y values on this graph? Total weight of sand at that time. So you pick an x value over here. The y coordinate of the point on the graph is telling you at that moment in time how much total weight has accumulated on the scale. That's the y coordinate. Whereas over here, the y coordinate is the rate of change at that moment. And so we're building this accumulation function on the right from the rate function on the left. And so our journey has been, how do we start? What do we do first to just make progress towards building the accumulation function? Pretend rate function made of steps. Constant rate of change step function. Why? Because that allows us to use the math of delta y equals k delta x. Constant rate of change. We can easily work with constant rates to get little bits of accumulation, delta y's. And so we use the step function, in this case r of left of x. And we can use that to easily sum up bits of change, k delta x plus k delta x plus k delta x. And that is the whole kind of big picture of that, our approximate rate of change function. Right? Our approximate rate of change function that gives us, based on the step function, gives us like a pretend accumulation function that has linear pieces, right? Linear pieces. And that's all about just summing up these bits of change by k delta x. That whole formula boils down to this. Okay? And so then, we have one step left, which we have not done yet, which we'll do today. And that is, now that we've got the approximate accumulation function, how are we going to get, we want the exact accumulation function. The exact accumulation function. The way this one is, all of our weights are, what? They're too low, right? All the weights we're getting in this approximate accumulation function are too low, because if we use left, the constant rates are underestimating the real rate. Do you see that? The constant rates are underestimating what the real rate is at the beginning, and it starts to catch up. So now here the rates are overestimating the real rate. But it was so far behind in this first part, it starts to catch up and finally catches up at the very end. Okay, so this is the journey we're on, and we just have step 4 is left. Only the last part 4 of the process left to talk about. So let's just kind of pick up where we were last time. Which was here. We were looking at we got here last time? We were looking at the formation of our step function using delta x of 0.3 and the left side approach. And so then as time goes by, that we are seeing, as x increases, we're seeing that step function being emerging, right? Point by point as steps. And then likewise, as time goes by, our approximate accumulation function emerging according to the equation that we built. And the last thing we did was to say, all right, let's look at x equals 1.4 and investigate a of how does this thing calculate a of 1.4. Okay, so let's just recap that real fast. So let's pause time here. We're going to pause time at 1.4. So here we are. So how is it that that equation calculates the accumulation at 1.4 seconds, or the total weight of sand on the scale at 1.4 seconds? All right. In other words, what are the coordinates of this point? X coordinate is 1.4. Y coordinate is exactly a of 1.4. Is that an exact amount of weight or an approximate amount of weight? That's an approximate amount of weight on the scale at 1.4 seconds. So how does it do it? So J means what? What does the value of J mean? J equals 1 is talking about the first whole interval, right? The first whole interval down here. And so when we plugged J equals 1 into this right here, we got R of 0. If you plug J, A equals 0 and J equals 1, this whole thing turns out to be R of 0. R of 0 times our delta X is 0.3. So what just happened? When you plug J equals 1 in here, you get R of 0. Well, R of 0 is the Y coordinate of all the points on the first step. It's that constant rate in the first interval. It's the pretend constant rate in the first interval. And so that's K1. That's K1 times delta X equals delta, say we'll call it delta Y, delta W1 for weight, which is like delta Y, right? And then J equals 2. Okay, you want Y? I was just calling it W for weight. So yeah, so this is like weight of sand is W. Okay, and then if you put J equals 2 in, J equals 2 refers to the second interval. When you put 2 in this expression right here, you get R of, not 1. R of what? R of 0.6, is that right? R of 0.3. And what is R of 0.3? Well, that's the rate at the left side of the second interval, which we're going to use to pretend to be the rate for that whole interval, times the interval width. And so what? We get a little bit more accumulation from this constant rate. That's what this part right here is doing. So for each J, interval 3, it becomes R of 0.6. That's the constant rate for the third interval times delta X equals delta W3. And then J equals 4. When you put J equals 4 in here, you get R of 0.9. R of 0.9 is the rate at the left side of the fourth interval, which we use to pretend to be the rate for the whole interval. And then what does this mean? Sum. It's a sigma. It's Greek sigma. So just think sigma sum. That means sum. So we're going to sum up all those bits of change or bits of amounts of weight and sum all those up. So I actually want to do that. Let's see. So I'm going to go to the R function. Where's our R function? R function's at the top. Here's the rate function. I think you did that in your homework, right? So we'll do R of 0, 0.2, 0.21. Okay, so I'm going to do each of these. So this R of 0 is 0.21. All right, so I'm just gonna erase and put 0.21 in there now. Okay, and then R of 0.3, 1.05. So what are these? The constant rates on the steps. And that's what that A does. For each J value, it gives you the constant rate on the step. Okay, R of 0.6, 2.95. Okay, remember that? And 9 is 4.73. So I think it was at 2.95. Thank you. And then 4.73. These are approximations to R0, R.3, R.6, R.9. Okay, now let's get values. Okay, so if you got a calculator, quick, just pick one. Pick one of those, 1, 2, 3, or 4, and do it. I got R 3.9. Let's see. 1.42. Anyone got for 1? 0.063. For J equals 2. 0.315. And number 3. All right, so let's do 3 decimal places here. 419. Do we have confirmation on those values? Okay, so now pick one of those numbers. Just pick one and explain to the person next to you what that number is. So pick one of these 4. Explain to the person next to you what is the value that number represent. Go. Yeah. Can I do what?
Basically, it's all graph. Maybe 5 is for the homework. 5 is my example. Oh, that's good.
But in that, maybe on the homework it's at 5, yeah. Where's Dima today?
I don't know.
Okay. Where's Gina Castillo? Gina Castillo. Not here. Okay, how about Aaron Cohen?
Yeah.
Tell me, which one did you pick?
The first one.
For the first one, 0.063. 0.063 what? What is that?
It's hundreds of pounds of sand per second. So that's the rate that you get. Like after in that interval, that's like how many hundreds of pounds of sand are going per second.
Okay, he said in the first interval, that's how many hundreds of pounds per sand you're getting per second. What do we think? Yes or no? Hundreds of pounds of sand per second. So you're saying that's a rate.
Oh no, that's the accumulation.
Okay, so we want to start again?
Yeah.
Okay, go again.
So that's the after the first interval. That's how hundreds of pounds of sand have built up.
Okay, now he's saying after the first interval has gone by, or say after 0.3 seconds,
Yeah.
how many hundreds of pounds of sand have built up on the scale? All right, now so who chose J equals 3? Who chose J equals 3? No one will admit it. Okay, I'll just call on somebody else. Okay, where is Sean Hollum? Sean.
I'll do it. I'm not sure. I'll do it.
Okay, Sean's not here, but go ahead. So what is 0.885?
0.885 is the amount of pounds that have been accumulated between the second and third interval. So the entire third interval is going to be that much weight, 88.5 pounds.
Okay, so he's saying during that third interval of time, 88.5 more pounds
Yes.
added onto the scale.
In addition to this J1 and J2.
So the 88.5, does that include this or not?
Yes. No, it doesn't include it, but it adds on top.
It adds on top of it, right? This is the amount of accumulation in the third interval of time, the amount of accumulation that we get. Okay, so what are we going to do with these numbers? Add them up. Anyone do that yet? Quick. As soon as you get it, shout it out. 2.682, and then at least a couple more people do it, and let's confirm that. Okay, good, sweet. Is that the total accumulated weight after 1.4 seconds? Why not? This is the total accumulated weight in how many seconds? 1.2. These are the whole intervals. This is 4 whole intervals, which would get us up to 1.2 seconds. So we still have a little more accumulation for the last part. So what's left of x right now? X is 1.4, so left of x is 1.2, r of 1.2, times x minus left of x, which is how much that partial interval lasts for. How much of that partial interval is there? 1.4 minus the left side. So how far into that last interval have we gone? 0.2 seconds, not 0.3. What's r of 1.2? Times point. So r of 1.2 times, not 0.3 now, but times 0.2. It's a partial interval. 0.861. Which is the little bit more accumulation we get for the last 0.2 seconds. And what are we going to do with that? Add it to this. And then we're going to get, that will give us A of 1.4 equals 2.682, the total accumulation from the 4 whole intervals, plus the little more accumulation from the partial interval. Shout it out. And what's the units on that? Pounds, hundreds of pounds per second. What's the units? Degrees Fahrenheit. Yes. What is it? What is it? So how many 100 pounds of sand are on the scale? 354.3. 354.3 at 1.4 seconds. Exact or approximate? It's our approximate based on our step function, right? Based on the step function, which is pretend. 354.3 pounds. All right, so now let's check it. Here we go. So we'll go to the A function. Oops. So here's our A function. I'm going to come and start a new line here. I'm going to do A of 1.4. Here we go. What does it do? 3.542. So we're off by, well, we're off by what? 1,000th, okay? And that was just our rounding error along the way here. That was just our rounding error, but that's close. Okay, so this is how the A function works. It sums up the bits of accumulation for the whole intervals, plus a little bit more for the partial interval. Okay, any questions on this approximate accumulation function? Super important. So we want to finally get to we want to get to the actual accumulation function. So we know that, and I showed you on the earlier screen, that there is some curved accumulation function here. That's the real one for the real red rate function. How are we going to get to that? Or maybe a better question is, how can we get closer to that? Lots of people already know. I saw you first. Make delta x smaller. Brock, what are you going to say? Okay, make delta x smaller, right? So if I make delta x smaller, let's just show the whole thing at once here. So if I make delta x smaller, watch what happens. More steps that are shorter, more linear line segments. So each time I make delta x shorter, what happens to the step function? It gets better. And therefore, what happens to our approximate accumulation function based on that step function?
More accurate.
Gets better, right? It gets better and better. So I go real small here. Okay, so now look over there at the rate function. The actual, the exact rate function is not being graphed there. What's being graphed there is the step rate function. And what do you notice about for delta x of 0.02? What do you notice? Those in the back. Can you tell the difference between the accumulation, the original rate function? Sure, why it's not turned down right now. Let's see. Oh, I think I've got it to automatically shut off here. There we go. All right, so notice there it is. The red graph is our exact rate. Make delta x smaller. Now I've taken the red graph away. You see those are still constant rates. Make it even smaller. Well, that's really small. I think there's one more in between there. That's not what I wanted to do. I wanted to do this. There we go. Is that the actual rate function? Those are still steps. They're just so small now that you can barely, we really can't tell the difference between the actual rate function and this step function. The delta x now is 0.005. And so how about this as an approximation for the accumulation? Good approximation? We're pretty much to delta x is such that we can't tell the difference. So yeah, it is still approximate theoretically, but it's so close that we can't tell the difference. Okay? Okay? So everything we've done so far, including a very small delta x, now is calculus. We just arrived at calculus by making delta x small. So calculus is everything we've done so far with a very small delta x. Why? Because we can get exact accumulation from exact rate. That's what calculus is able to do. So we've got an exact rate function. We build the exact accumulation function. What makes that possible? A very, very small delta x. So small that we can't tell the difference between the approximate and the real. It's close enough that we just call them equal. That's the idea. Okay, let's watch it again. This is huge. Okay? Good approximation or bad? Horrible. Horrible, right? The step deviates greatly from the actual rate function. Gooder.
Better? Gooder is not a word.
Thank you.
Well, better.
Okay, and so we get to a point where we got small intervals, really close, and then here's 0.005, virtually the same.
Very nearly perfect.
Very nearly perfect. And so we call it a day, and we say, we've got it. We've got the actual accumulation function because our delta x is small enough. We've got it.
Could you go even smaller than that?
Yes, I could, but it would change the accumulation function so little that it doesn't matter for our purposes. Yeah.
So theoretically, it'll never be exact, no matter how much you change delta x. It'll never be the exact.
If delta x is a finite, yes, it's still an approximation, but we get to the point where we call it small enough that for our purposes, it's so close that it's the same thing. Okay, so this is the beauty of graphing calculator, that we can put the functions in as functions of delta x. See, we built the left, you know that function. There's step based on left, right? And then there's a. And here's the beauty of graphing calculator. We can put these functions in as functions of delta x, and then all we have to do is change delta x, and we can make it exact from approximate. Okay, so we're using the power of the technology to our advantage. Okay, because what we just did with the 4 full intervals and then adding the little partial interval. You want to do it now for a of 1.4? We'd be here for months, right? We'd be here for months calculating these little bits. Okay, but let's use the technology. Let's understand what's going on. Let's use the technology to do it in 10 seconds, right? 10 seconds we can make delta x small and see the exact accumulation function. Please.
How'd they do it before, like the computers and stuff?
Well, even though they didn't have the computers to animate it, they knew this, right? So say they developed the mathematics, the equations, and they could sketch graphs and prove that this was going to happen. But we just have very nice visuals of it with the technology. Okay, so let's summarize this. We have arrived. We are doing calculus. We've been doing calculus, but now we've kind of sealed the deal by making delta x small. So this is our fine-tuned accumulation. So here's our accumulation function, which is, what do we say? That's essentially summing up a bunch of k delta x's. We've worked it out, right? We just worked it out with the 4 full intervals and the little small interval. But essentially, you're just k delta x plus k delta x. How do things accumulate? Bit by bit by bit. Means sum up the bits, and that's what that function is based on. So when delta x is very small, we're going to represent delta x as dx. So dx means delta x extremely small, like molecularly small or atomically small, the distance between electrons in an atom.
Or could just be the size of an electron.
Yeah, that would do great too. So what is this? Our function then becomes, everywhere there's a delta x, we write dx now, and we know, okay, now we're talking about super small values of delta x. So then what about this partial interval? When things get that small, what's the difference between the lengths of whole intervals and the lengths of partial intervals when things are that small? There's really no difference, right? So we don't need the partial interval anymore because our intervals are so small anyway that a partial interval is just like also small, right? And this is essentially the rate function, dx, okay? So this is essentially, now we're looking at kind of thinking about maybe instead of a bunch of rates, we're thinking of every rate on the function times dx and summing those up. So rather than these steps, these constant rates, it's like every single rate as it changes times a super small interval. Okay, so this version of AX is, we say, indistinguishable. When delta x is small enough, it's indistinguishable from the precise, the real, true accumulation function associated with R. So we have a simplified notation for that. So here's our simplified notation. We said it was integral calculus. It's an integral. Okay? So this is, we say, the integral from a to x of r of t dt. The integral from a to x of r of t dt. That thing right there, that f of x function, is exactly the same function as the a of x function with a super small interval. It's exactly the same function. It's just a more compact, nicer, convenient notation. But these two functions are equivalent. This is not, because this is for larger delta x. Okay? But when you make delta x very small, we're using dx, then this function is absolutely equivalent to this. It's just this is more friendly to work with.
And t is what?
Okay, so we're getting there. Okay, so what does it do? It outputs the accumulation of a quantity with a rate function r as x varies from a to the current x value, which is exactly what this did, right? So what does it output? The output f of x is the accumulation of a quantity whose rate of change is r, rate of change function is r, as x starts at a and varies up to what? The input of the function, the current value of x. Go back. Go forward. I want this one. So how do we see, so this new notation, I'm coming back to it. How do we see that it's the same? So what's going on here? So where are the parallels? You know, if it's the exact same function as this, it should express the same thing that this one expresses. So what parallels do you see between this and this? What did we say? This one is essentially this, right? So how do you, maybe we should try to compare these two. How do you see this thing here showing up in this new notation, this integral notation? So what's one thing that you see that's the same? R, the R function, right? So here is R. Here is R. Very good. What else do you see? Okay, so how do things accumulate bit by bit? And each bit is calculated by rate times change in x. And so that's what we're doing. We've got rate k delta x. K delta x, but it's just now delta x is super small. There it is. K delta x. What else do you see that's the same? Summation, right? So here we got sigma. What do we have here? This thing right here, the integral symbol. Do you see it looks kind of like an S? This is actually German S. So this is like Greek S, and this is German S. It's the integral symbol. S for sum. So we're still, what? Summing up a bunch of bits of accumulation. They're just a lot more, and they're a lot smaller bits, right? A lot more bits and a lot smaller. But it's still, we're summing them up. Just like we summed for K1 and K2 and K3, K4, and then we sum the little additional. We're going to sum up all the bits of accumulation. Okay, starting at A, right? Starting value of x. But then that amount of accumulation is a function of where you stop, right? So we built an accumulation function. So we get all the values of accumulation for any final x value that we pick. So that's our input. Our input is where we're going to stop accumulating. It's the input. The input is where we accumulate to. So what, like in our example that we just did, what was the value of the input? We did 1.4 seconds. So that would be like f of 1.4. F of 1.4. 1.4 being the final value that we're going to accumulate to. But the function then gives us the whole thing, right? We could pick any input value and it would give us the accumulation to that point. The beauty of a function, right? Okay, so this integral notation, again, is a representation of what this essentially is, which is a sum of a whole lot of very small bits of change. A sum of a whole lot, a sum of S, a whole lot of very small bits, K delta X. We're still talking about K delta X here. Okay, so the question has come up. So we've got X here, Y, T. Okay, what's going on with T? So let's go back to graphing calculator and kind of work with this and investigate Y, T. So the first thing is we can, so I'm going to make delta X a little bit bigger again. That's fine. The first thing is we can do integral notation on graphing calculator. Here's how you do it. Control Shift I. Control Shift I. So I'll just start it again here. So I've got it there, but I'll just do it again. So we're going to build this. So F Control 9X. So capital A of X, that's our approximate accumulation function. That's that bad boy formula. And then capital F of X is our exact accumulation. That's our integral function. So we go equals Control Shift I. And the integral comes up. So we want starting from A, this would be A down here, but for the sand example, A was 0, to what? To X of capital R, and I used T in the formula. So so it gives you the integral kind of template, and you have to change it to do what you want. So we're going to do the integral function from 0 to X of R of T dt. Okay, down here in this one I used U. Okay, we'll talk about that in a second. So what did we do? We did A of 1.4. I'm going to come back here and do A of 1.4. And did we see that that was an overestimate or an underestimate? So let's graph them both. Here, let's graph. Oh, no, it needs to be 4. Okay, hold on. Okay, so the pink one was, that's the approximate accumulation. Let's just go to point 3. Okay, so here's the approximate example we did with delta X of 0.3. And so I'm graphing here's 1.4, X equals 1.4. Here's our A of 1.4. So that point, 1.4 seconds, and the total accumulated weight, approximate, at 1.4 seconds. That's what that point means, right? At 1.4 seconds, A of 1.4 is the total approximated accumulation of weight at that moment. Overestimate, 3.54. That's what we got. Overestimate or underestimate? So here's our exact. So here's the capital F function that I graphed, which is our integral function, which we know is virtually the same as our A function when A is very, very, very small. Essentially the same function. Okay, so if I do F of 1.4, I'm expecting what kind of value? Compared to A of 1.4? Larger. There's the true accumulation of weight of sand. Here's 1.4 and F of 1.4 up here. It's because we had all this underestimation of the rate of change, which means an underestimation of weight at the beginning. Now it's an overestimation, but it still has all that to catch up to, right? So it's still, the approximation was still too low. And we're off by about, what, 50 pounds. We're off by half of 100 pounds using the delta x of 0.3. Okay, so that's how you can, you can actually put functions in, integral functions in the graphing calculator. You can create this integral function, and then to graph something on the right-hand side, have you done that in homework yet? Use the primes, so that's what I've done. Y prime equals f of x prime. Opens up a second graphing window where now I can graph that exact accumulation function. Okay, so now I have another function here. What's the point of, here I've got u, and then before I told you it was t. So why can't we just put x? Why can't we just put x? So let's investigate that. So here's a function based on, that's the same thing, but now I'm going to use x here. So let's look at g of 1.4. Let's write it out. What would g of 1.4 be? G of 1.4 would be the integral from 0 to 1.4 of what? R of 1.4 dx. What's that going to do? So talk to the person next to you. What will that give you? What will that give you? And why is it not what we want? Okay. Here's the point 1.4, R of 1.4, right? Correct? So what will this do? What will this calculate? From 0 to 1.4 of what? This is going to be a bunch of little, bits of accumulation, but based on what? Which rate? These rates? The red rates? Because we want it to be, to get the bits, we want it to, for each bit, we want it to reflect the true rate at that moment in time. Does that do this? No, what is this? This is just a constant rate of R of 1.4, like this. So for all the way from 0 to 1.4, what rate is it going to accumulate at? Not the changing rate, but this constant rate of 1.4. If you construct the function this way, it's going to plug your input value into the rate function in there, and you're going to be accumulating at a constant rate the whole way. Do you see? So what do we need? We need something else we need a different variable that represents, it's still representing x, but x changing from 0 to our final point. If we use x, it's reserved for where we're going to stop accumulating. But to calculate the accumulation, we need something else that's giving us x changing all the way from a to x. And if we just use x again, then we're just going to be plugging in the final value into the rate and getting a constant rate, R of 1.4, the whole way. So do you see that this doesn't work? So if I put in G of 1.4 now, I'm going to get something different. It won't be right. G of 1.4. It's coincidentally close. Only coincidentally. It just happens to, that constant rate happens to kind of balance out being an overestimate and underestimate. It's like a huge overestimate and then underestimate, and that kind of balances out. And so we coincidentally, in this case, get close. But this is the wrong function. We don't want to plug in the final value of x into the rate function. We want something else that's going to give us all the changing rates up to the final value. So that's why we need that some other dummy variable. It could be t, it could be u, it could be v, it could be b, it could be a. It doesn't matter, just as long as it's not the same as that. The problem comes when you use the same variable that you're stopping with in the rate function, which will give you a constant rate for the whole interval. Does it make sense? Okay, so let's practice some. We need to practice with these interpreting these integral expressions. There are my kids peeking through my windows. Did I ever show you them from the first day? Remember we did the quiz? I never showed you?
Oh, yeah.
These are my wonderful kids.
You have to guess how old they were.
Yes, you had to guess. All right, so where are we? What's the meaning? Okay, worksheet. We're ready. Okay, so here we go. Here's a bunch of integral expressions. Super important. So when you see these integral expressions, you can identify them. So determine, first of all, does it represent a valid accumulation for its rate function? We just talked about that. If you have that matching upper bound of the integral and input in the rate, you're going to get a constant rate for the whole thing. No good. Okay? Identify all the parts of the expression by their meanings. Introduce function notation to rewrite it as a definition of a function or a particular output of a function. Okay? And then describe the meaning of the expression as a whole. So you got 4 things to do for each of these. And I want to really get you understanding this by the time we leave. We got, 9 minutes. Here we go. Talk about it, get your questions answered, and then we'll talk about them at the end. We'll do the first one together. Is it a valid, we'll do the first one together. Is it a valid accumulation function?
Yes.
Yes, because we've used a different dummy variable for x varying from 4 to the final value x. Okay, so identify all the parts of the expression. F of t is what? The rate of change. dt is super small delta x. Okay? F of t times delta t. What is that? A super small bit of accumulation, or super small bit of y. What's the integral sign mean? Sum. Sum up a bunch of super small bits of accumulation. Starting at, ending at. So it's a function of where you're going to end. It's a function of where you end. Okay? So let's make, we use function notation, we use our f. So it's going to be capital F of x. We just made it into a function definition where capital F, the output of capital F is the exact accumulation. Starting at 4, accumulating to the input x at a rate of f of t, or f of x, at a rate of f of x. Okay, go. So you do the rest. That's what you're doing.
The next one is northeast of
Well, it's a valid function, but won't do what we want it to.
Yeah.
That's right. Just go on.
Right, next. I mean, it works as a function. The bottom left is a to x, that's no other x variables inside the equation. That's what it is. It's a balanced function. Then we have 2b minus that's going to be the right. Yeah, so it works, but we don't know 100%. But yeah, we're going to say we're going to have this function in x. Same thing. Zero to a doesn't have x. Because a is 0 to x. Right? Or they just 100% works. We have 0 to a, that's it. So x works. This constant is defined as
So that's what happens. It's the left part is more of that. It's in part of the system.
So yeah, so it's different. It works.
X is 8. X is 8. So this. If X is 8, this is basically filling in the variable, and these are also X. Oh, can it be? Or it doesn't have to be X, the original.
I mean, X is just a name.
Okay. I guess so. Just finding out the original. I thought that this was like, it has to be X. But I guess
I mean, it's a chance of being
oh,
you
okay.
have to have something different there.
Alright. Yeah, that makes sense. I just don't. Yeah, that's.
So I agree, it is different than what you have up here.
Oh, okay. That's the wrong one. Yeah, I guess it. I guess that makes sense. I guess I just assumed that. I just assumed that it I haven't gotten that far. I was only.
How about this one? Good or not? So we'll call this one F1. Because this is different, we'll call it F2. This one starts accumulating at what value? A up until the input, right? The input of the function is where you're going to stop accumulating. The ending right-hand point where you're going to stop accumulating. And we're good because we've got a different variable representing. So V still represents X, but it represents X changing from A to the final value of X. That's the key. V is still X, but it takes on all the values of X between A and X so that we get the changing rate. according to this function. Does it make sense? Okay, what about this one? Good or not?
Yes.
Yes. Okay, so, but we can't, so we want it, so if F3 now, we got to do it in terms of something else. So we'll do F3 of C. And so then what is this, so F3, so we've got F3 of C, then this thing is expressing F3 of what? 8. So it's like we're talking about some function and we're plugging 8 into it. So is this whole expression a function or a value? It's a value. It's an amount of accumulation starting at 0, ending at 8, according to that rate function. So that whole thing is not a function. It's a particular numerical value. We could put it in graphing calculator, and it'll say equals, and it'll give us a number. Don't have time to do it. Okay? Same thing with this. So this is like some F4. Is it F4 of A? No, let's call it F4 of X. Okay? And it's like this is then F4 of what? 15. Last one, good or not? Exam is next Wednesday, and I will put up prep material today or tomorrow.